Wave motion, right? Wave motion for this unit, right, in terms of simple characteristics is going to be very, very basic. It's something that I hope you've seen before in your old physics class, right? In freshman year,
Yeah,
probably, right? And so the most fundamental thing that I want to make sure everybody's clear on is what a wave is, right? What is a wave? What is a wave?
Well, when you're in the ocean, and no.
Oh my God,
Yeah, okay, that's fair. Huh?
Is it like the movement of energy?
Right. More specifically, it's the movement of energy. That's exactly right. It is not necessarily a displacement of a physical object, right? It is simply the translation or the movement of energy. Try and get that to not be blurry. That's better. All right. Translation of energy, right? So the easiest example is this giant spring that I have hung up here on the ceiling, right? Whenever I go like this, waves move back and forth from the corner of the room to the other side. Look, you can still see them going, right? But what's important is that the energy moved from one side to the other, but the actual spring didn't change where it is in the room, and where I input didn't move that part of the spring to the other corner of the room, right? What you track is actually a chain reaction of motion, right? I hit that piece of spring, which caused the piece of spring next to it to move, which caused the piece of spring next to it to move in a chain reaction that happens very, very quickly. All waves are that, right? On the ocean, wind or a boat or an earthquake or something caused the water to vibrate. And because the water is next to other water, that vibration perpetuates through the system. As it spreads out, the energy decreases because it has to encompass more of whatever that system is. So generally, we expect the energy of a wave to dissipate as it goes farther out. Does that make sense? Go.
With dominoes, like, because you said like one thing knocks the other, but that's not like a constant.
Realistically, dominoes is an energy wave that is non-repetitive, right? A periodic wave, something that repeats over time, is due to the fact that when I input that energy into the spring, that piece of spring vibrates more than once, right? And so we end up seeing multiple waves, right? Multiple waves. But a dominoes would be a good example of a singular wave. Very similar to if you were to watch one singular breaker at the beach, right? That one wave happens and then stops. Does that make sense?
Like a tsunami.
Like a tsunami is a good example. Yes. Okay. That being said, there are two types, transverse and longitudinal. Transverse, I lost an S somewhere in there, and longitudinal. Sorry. Fundamental difference between these two is simply the direction of the part of the whatever it is that's vibrating, right? Of the medium in some cases, and in other cases just whatever it is that's generating the wave, right? And so we think of a transverse wave as looking like this, right? Where we're tracking the energy as the vibration of whatever it is occurring, right, is actually happening vertically or perpendicular to the direction of propagation, right? We track the energy as moving across the room, whereas the actual thing that is vibrating is usually vibrating up or down or left and right, perpendicular to that direction. So the spring is an example, the ocean is an example. The water goes up and down, but the wave moves horizontally, right? So in a transverse wave, vibration is perpendicular to propagation. Propagation is a vocabulary word which is the direction of motion of the actual energy.
Can you say that one more time?
Vibration is perpendicular to the propagation. Propagation is the direction of the energy, not necessarily the medium. Transverse waves will be springs, cables, ropes, water, and most specifically and most interestingly, light. Light is a transverse wave by definition because of the fact that a photon is actually a perpendicular transverse wave in amongst itself. Light is a unique case, and we will talk a little bit more specifically about that later. What's interesting about that is light does not require something to vibrate. The actual photon is the vibration that generates the transmission of the light, right? So light is able to propagate itself. This is a special case, and this is very important because light is able to move through a vacuum, right? The most fundamental example is anything in space we can see because the light from that object is able to move through the vacuum of space because it's its own vibrational source. That make sense? Not really, but it's good enough, right? Longitudinal waves, on the other hand, vibrate more like this. Right? And that looks very strange, but if you can imagine that this was a slinky spread out, these areas would be where the spring has been squished together, and then upon release, because of it being elastic, it would spring out, spread out, which would then cause a different area to stick together, and that would cause it to vibrate back and forth, back and forth, back and forth like that, perpetuating that compression. It's called a compression wave for short, right, as opposed to a longitudinal wave. And that's important because compression implies that something has to be compressed. So in a longitudinal wave, we have to have a medium in order to do the compression. This does work with a slinky or a spring, right? It's much harder to see. If I squeeze this way and let go, right, you still get a wave. That is a longitudinal wave. The actual vibration is parallel to the direction of propagation. But again, the spring itself is not moving over there. So locally, in a transverse wave, the spring goes up and down, right? And that causes the wave to propagate horizontally. Locally, the spring vibrates this way, which causes the wave to propagate horizontally, right? So in a longitudinal wave, those two things are parallel. But more importantly, in a longitudinal wave, there has to be something to compress that has the elasticity to bounce back. The most common example is sound. When we speak or play music or do anything, that sound has to compress a medium in order to propagate that energy outward. Generally, that's air for most purposes, but it can also be water, right? It can also be solids, right? We can hear the train coming by putting our ears to the track because the vibration will propagate through the steel of the tracks, right? And it actually propagates better through the steel, which is why you can hear a train coming before you can see it, because the sound will travel very, very well through the steel. Go.
Was an earthquake an example?
An earthquake does follow longitudinal waves, yes, but you're also familiar that some earthquakes cause cracks. So an earthquake can actually do both, be transverse and longitudinal. So we don't want to get too confused as that being a definite example. Nevertheless, what we end up with is a movement of energy over a long distance. And as long as the medium itself does not change, right? So we don't have things like where the spring gets thicker or connects to a rope, right? Or something like that. As long as the medium is one consistent thing, then the speed of that energy is a consistent value, right? And so that means that speed is constant.
Let's just go for both.
For both, yes, exactly. Speed is constant in a given medium, as long as the medium doesn't change, obviously. And we'll look a little bit more when we do sound and light in more specific terms for how the medium can have an effect, right? But for now, that's a fundamental explanation of wave motion, which means that all wave motion is going to obey the most fundamental speed rule, which you already know and you demonstrated to me, right? Which is V equals d over t. Right? That being said, within a given wave, there are some terminology characteristics important, right? If I had a wave that looked like this, right? This is a graph of time and displacement, right? displacement being how far that particle has moved from a given position. And so what we end up with is it goes up and then it goes down from an initial point, right? The maximum point in both directions is referred to as A. A stands for amplitude, right? Amplitude is the maximum vibrational displacement.
Amplitude is the maximum.
Displacement. This is important because that means that this graph can represent this wave and this wave. Because in both cases, the medium is vibrating from an equilibrium position, right? From the middle, up and back down, over, indefinitely. Here, this piece of the spring is vibrating some amplitude this way, and then springing back some amplitude that way, over and over and over and over and over and over and over. Which means that if I just graph it as displacement, it doesn't matter if the displacement is vertical or horizontal, it still represents the same terms, right? This is why, in general, wave motion can be thought of as just V equals d over t, regardless of what type of wave it is, which actually makes the math much more simple. Does that make sense? Yes? Okay. So if that is true, then the other thing we have to pay attention to is the repetitive nature, right? The periodic nature of a wave. If we have a wave where we actually see multiple peaks in this sense, right, then we know that the initial energy is actually being repeated, right? If this was just a singular input, the wave would look more like this. Over time, it would be over here, right? Further on, it would be further on down the line, right? It would just, oops, I'm sorry. It would just move further down the spring. Right? Since there is an actual pattern in most cases, we know that that input energy is continually being input, which means we need to isolate one wave only in order to functionalize the speed, right? And I think you already know how to do that. You know that this point and this point share common characteristics, right? They have the same displacement, 0, right? But they also have the same trend. In other words, increasing. Right? We could think of it as concave up versus concave down and inflection points, right? Depending on how good your math vocabulary is. Either way, what you know is that there is actually a piece where I can mark off from here to there that will be repeated in segments down the line, right? So one complete oscillation all the way up, all the way down, and back to the original starting point, right? That is called a cycle or an oscillation, right? And any periodic wave will then just be multiple cycles in a given time frame.
Spell oscillation.
OS. CILLATION. Oscillation or cycle, right? That's a no. That being said, if I were to graph that, right, then I know that if I measured the length, right, and that would just be on a different graph because this is on time, but if I actually had the spring, and this were moving like this, from here to there, right, just from there to there, is referred to as a wavelength, lambda. Wavelength is the physical distance that that repetitive pattern allows the energy to cover before the cycle repeats.
Can you repeat that?
The wavelength is the physical distance that the energy travels before the cycle repeats. Or the displacement during one cycle. The second term is then back on this original graph, the time it takes for the cycle to occur, right? In order to go from the initial equilibrium position to the maximum, back to the equilibrium, down to the negative maximum, and back to the equilibrium. That takes a certain time frame, right? That time frame is called a period, right?
It's like a sine graph.
It's exactly like a sine graph, yes. Sine or cosine, and we will look at both. You're exactly right. Period is simply the time for one cycle. Shoot. So obviously wavelength is lambda. Period is a very specific measurement of time and therefore is given capital T as a variable. Therefore, this is the math symbol for therefore. 3 dots in a triangle. Yes? Seen that before? Good. Therefore, V equals d over t as related to normal motion, translated into vocabulary for waves, is the velocity of a wave is equal to lambda divided by period. It's basically just a translation from our typical terms into wave-based terms. Beyond this, it's basically plug and chug for calculating wave speed, right? Since wave speed is constant in a given medium, this is a constant formula. So as long as you can identify the wavelength, measure the period, then this calculation is fairly straightforward. There is one caveat that's important to know, which is the term frequency. Frequency is given lowercase f. And frequency is exactly what the word means, how often something occurs, right? And so in this case, frequency is the number of cycles per second. Realistically, we already have this term, right, in the inverse function. The time for one cycle is defined as a period. The number of cycles per unit time is frequency. Therefore, frequency is simply the inverse of the period. In society, in real life, frequency is often the term that is utilized as opposed to period because it makes more logical sense to us to think about a certain number of hertz as opposed to a certain time frame for one cycle. The easiest example is any kind of processing speed in a computer, right? Computer has a certain amount of gigahertz or a certain amount of, like a CD-ROM has a 32 hertz rotational rate, right? That's the fact that it goes around 32 times per second, right? Because the time it takes to go around is so minute, right? To list it as the time it takes for a CD to go around as 0.00001 seconds is just ugly in terms of the list. So instead, it's 32 hertz. So it's important to note that this, in terms of units, is 1 over seconds, right? Which is equivalent to hertz, Hz. That's the unit of frequency, which is in SI is just 1 over seconds. But you will see that a lot. So this can then be translated as lambda times f as opposed to lambda divided by t.